Chemical Kinetics Part 6. We're going to take a look at integrated rate laws and consider derivatives, integrals, and understanding graphs in relation to calculus. You don't have to know calculus to be able to do chemical kinetics, but I think it is worthwhile to understand why calculus works here and to at least trust that the integrated rate law expressions come from somewhere. So let's say we have a single reactant A forming products as our reaction. The differential rate laws for zero first and second order reactions would look like this. Each one of these differential rate law expressions would be equal to a negative derivative or a negative instantaneous slope on a concentration versus time graph. Now, if you can't calculate a derivative in calculus, that's okay. You could graph out the concentration versus time graph. To get the instantaneous slope, or the slope at a point on the graph, you could draw a tangent on your graph, measure the delta y and delta x to that tangent line, and use that to calculate what the slope was at that point. So you wouldn't necessarily have to do the derivative if you were willing to build the graph. All of these differential rate laws relate the rate of a reaction to the concentration. Let's take a look at some graphs and go from there. Again, we have a single reactant A forming products in all of these. That's our reaction. And we can say that the rate of reaction is equal to a negative of the derivative of concentration over time, or the instantaneous slope at any point on the graph. It's a negative of that slope when we're graphing out concentration versus time. Now we could flip this around and say that the slope is equal to a negative of the rate. Okay, so for a zero order reaction, the rate's K. If we graph out concentration versus time, the slope would be a negative of the rate, or negative K. Again, looking up here, if the rate is a negative of the slope on the graph, the slope is the negative of the rate. So the rate's K, it's negative K. Negative K is a negative constant number, so we'd have a line that's angling down that's straight. Straight line indicates constant slope, and angling down is negative. All right, let's take a look at a first order reaction. What might that graph out like if we have concentration versus time? Again, the slope is equal to the negative rate. The rate is equal to K times the concentration of A, so the slope is equal to negative K times the concentration of A. I have the concentration of A axis here, the y-axis, divided up into 4 increments. If we go to the very top, where the concentration is the biggest, then we would see that the slope would be the biggest. That would be the steepest line. If we go halfway down the concentration axis, we have concentration diminished by 1/2. The slope would diminish by 1/2. It would be half as steep of a slope here as it was there. And if we go down 1/4 of that initial concentration, the slope should diminish by 1/4. So we would see a curved line when we have a changing slope there. Let's take a look at what happens with a second order reaction. Now again, the slope is equal to a negative of the rate, right? Rate's negative slope, slope is negative rate. So the negative rate here would be negative K times the concentration of A squared. Let's look at this point where we have big concentration. A big concentration squared is going to give us a real big slope, so we're going to have a really steep line here. And then let's take a look at this line down here on the other end of the spectrum where we have a really tiny concentration. A tiny number, say like 1/8 squared is 1/64. That's going to give us a really tiny slope. So we're going to see really drastic changes when we have big concentration, very steep slope, and when we have low concentration, very flat slope. There's going to be like this dip in the curve here that we're going to see. All right, so we could, I guess, collect a bunch of data points for concentration versus time. It would be problematic to do that for reactions that happen very fast, but we could do that. So if we did collect data points and we did graph these out, let's take a look at what would happen if we were to graph the rate versus time. Now remember that the rate of the reaction is k for a zero-order reaction. So that means that no matter what, the rate of the reaction is going to be constant. It's just going to be all the way straight across, constant k at any time. No matter what the concentration is, no matter what time is going on in that reaction and how the concentration is changing over time, it would have no effect on the rate. So flat line. In a first-order reaction, we can assume that, it's a reactant here, so A will be getting smaller and smaller as time progresses. So we can say that as time progresses, we would see some kind of a downward angling line. Remember that in a first-order reaction, the rate is equal to the concentration times the rate constant. The concentration will be getting smaller as time progresses. So we're either going to see a straight line or some slightly curved line here for a first-order reaction. In a second-order reaction, because the rate is equal to concentration squared, any changes in concentration as A diminishes would square and change the rate. So the rate will diminish more drastically. And we're going to see definitely some kind of a curve here and probably a bigger curve than we would see for any first-order reaction. Now, before we move on, we can also see why we actually have this idea that we always want the rate to be a negative of the slope of this graph. Because reactants will always have diminishing concentration as they progress, a negative slope for reactants would mean that if we made the rate equal to a negative slope and we graphed out rate, the rate would graph down in this quadrant, down below the x-axis, where the y values are negative. Well, we don't really want to do that, right? We want to graph out rate up in this quadrant. So the slope on a concentration versus time graph is always going to be negative when A is forming products. And we make the rate a negative of that slope. So a negative of that negative slope makes a positive. So that's why we make that rate positive, so that we can graph it out up there. So, do we really have to do all this graphing, though? Well, not necessarily. It turns out that if you want to relate concentration to time, that you can just use calculus. So in calculus, a derivative, dy dx, would give us the slope of a y equals f of x equation. And an integral, and this is the format of an integral, would give us the area under a curve of a y equals f of x expression. Now that's really important to us when f of x is some type of a derivative itself. We could say that the integral is the antiderivative. So let's see what that really means. So just a quick bit of calculus here with graphs. The slope dy dx, or the derivative at any point on the graph, the instantaneous slope, is a ratio of the differentials, where dy is the infinitesimal or differential y, infinitesimal change in y, differential y, and dx is the infinitesimal change in x, or the differential x. So the derivative gives us the slope at any point on the curve. Now the integral tells us the area under the curve. All right, so let's take a look at a few basic calculus equations here. We're not really going to get into any heavy-duty calculus here, but I do want to make the point that there are specific rules that you follow in calculus, and here's just a couple of them, just for fun. Let's say that we have some kind of a line expression here, y equals x to the n power. If we were to do a derivative of that, we would say that dy dx is always going to be n times x to the n minus 1 power. So if y is equal to x squared, dy dx would be equal to 2x. If y is equal to x cubed, dy dx would be 3x squared. Here we take the 2 and put it in front, and then 2 minus 1 is equal to 1, so it's 2 times x to the first power. Here we take the 3 and put it in front, and then 3 minus 1 is 2, so it's 3x to the second power. Now, if you don't know any calculus, it's fine. But there are some rules that we use. That's called the rule of powers. Here's something that has to do with integrals. This is a rule with integrals and powers. If we say that we have y equals x to the n power, then the integral, and this is the integral sign, it looks like an elongated s, of x to the n dx, and that's the format we write that integral, right? X to the n is the y expression, dx. We would say that's equal to x to the n plus 1 power divided by n plus 1 plus a constant. We call that the integration constant. So, for example, the integral of x squared dx would be 1/3 x cubed plus c. The integral of x cubed dx would be 1/4 x to the 4th plus c. Now there are a lot of rules, and that's why you would take calculus. So you don't have to do all the graphing, and you can just plug those rules in. So let's take a look at a zero-order reaction. Now just to remind you, a zero-order reaction has that the rate versus time graph is a straight line, and a concentration versus time graph, I guess this is a flat line, right? This is a straight line at an angle. Rate versus time is a flat line. So let's take a look at an example. Let's say we have a line graphed out here that has this line equation. Y is equal to 25 minus 5x. If we graph that out with these y and x-axis values, concentration versus time graphs out like this. And we would say that the slope of this graph, or rather the negative of the slope of the graph, is equal to the rate of the reaction, or the rate of change of the y value, I guess, in general. So we could say it's negative delta concentration of A divided by delta T, or negative derivative A divided by derivative of concentration divided by time. Now, since this is a straight line, it's really easy to do. We can just say that the instantaneous slope at any point is going to be equal to the average slope across the whole line. So we can take the final concentration, which is 0, minus the initial concentration, which is 25, and that would be our delta y, or delta concentration of A, or negative 25, right? 0 minus 25. And then the time goes from 0 to 5, so the change in time is 5 seconds. Now a negative of negative 25 is positive 25. 25 divided by 5 is 5, so we get 5 molarity per second. Remember that we put that negative there because we always want the rate by convention to be positive. So we'd say that the rate of the reaction is 5 molarity per second. Now if we graph out rate versus time, we would just graph out 5 molarity at every time interval. So the area under the curve is the integral. Now this is an easy area to calculate because it's a square. We can say that the area of the square is equal to the length times the width, right? The length times the width. So it's the y-axis times the x-axis. It's the rate times the time. Rates on the y-axis, times on the x-axis. Notice that when we do that, our total change in rate is 5 molarity per second. Our total change in time is 5 seconds. 5 molarity per second times 5 seconds, seconds cancels out, we get 25 molarity. So that means that when the reaction progresses, we have a change in 25 molarity for our concentration. So let's take a look at that derivative graph a little bit more closely. Let's take a look at this left-hand graph here. And let's do that with a little bit of calculus. So we would say that this is the expression y is equal to 25 minus 5x, right? For the left-hand graph, that's the line equation. So we could say dy dx, or d dx of that y expression calculates out to be this, and if you know your calculus, you can follow that along. The derivative of any whole number is constant, or is, the derivative of any number there is constant, or 0 rather, and then we could say that negative 5 dx of x would be negative 5 times 1. So negative 5 times 1 is negative 5. So the slope of that line is negative 5 molarity per second. Well, that's what we get here, right? A slope of negative 5. And remember that we said the rate is a negative of the slope, so the rate is a negative of that instantaneous slope, so it's 5 molarity per second. Now, we were able to do that with a straight line before, and here we can do it. If the line were curved, we would know the rate at any time on the line as well. So this is how you do a derivative. A derivative tells us about the rate. Actually, it's a negative of the rate. It's a ratio of the infinitesimal change in y divided by the infinitesimal change in x, or dy dx. It's a ratio of the differentials. dy is differential y, dx is differential x. And it's the slope at any point on the graph. It's the instantaneous rate of change of molar per second, or whatever variables on the y-axis. So if we had meters here, it'd be meters per second, and that instantaneous rate of change would be velocity. Okay, so let's take a look at our other graph now with a little bit of calculus. Let's take a look at our zero-order reaction that we looked at here, found the area under the curve, which is really easy to do when you have a nice flat line curve like that, but let's see what that would look like with some calculus. Using calculus, where our equation is that y is equal to 5, we would do an integral from 0 to 5, because we would like to know the area under that entire range of values from 0 to 5 of 5 dx. So we can factor out the 5 and say we have the integral, that's the integral sign, from 0 to 5 of dx, which is equal to 5 multiplied by x from the lower limit of 0 to an upper limit of 5. So x at 0 is 0, x at 5 is 5. So 5 multiplied by 5 minus 0 is 25. And notice our units. It's easiest to do units here. 5 is the y value. That's molarity per second on the y-axis, right? So the units for 5 are molarity per second. X dx has to do with the x-axis, which is in units of seconds. So when you multiply molarity per second times seconds, you get molarity. This gives us the integral, or the area under the curve, for any equation y equals f of x. The sum, and the reason that we use that kind of elongated s there for an integral is because it really is a sum of all of the products of f of x, which is the y value at any point on the curve, multiplied by dx, the infinitesimal change in the x value, or the value of x at every point along the x-axis. And that's done over an interval that's summed up over the interval from a lower limit of x equals 0 to an upper limit of x equals 5. So what we can say then, looking at that graph here, if we have rate versus time, we could divide this space up under the curve into an infinite number of rectangles, going from 0 all the way to 5, a lower limit of starting at 0, an upper limit of ending at 5. The height of each rectangle would be equal to f of x. In this case, the height is equal to 5, measured in molarity per second. The width of each rectangle is equal to the infinitesimal width, dx, the infinitesimal change of x. So the area of each rectangle is the height times the width. So if we integrate from 0 to 5, from the lower limit to the upper limit of f of x dx, we get the area under the curve. And notice what's happening with our units here. Molarity times seconds or molarity divided by seconds, times seconds, is going to give us units of molarity. It's going to give us the concentration. So if we integrate, we can figure out the concentration. Well, what if we don't have a graph that's a flat line? What if we have a graph that's at an angle like this? Can we still do an integration? Well, this is why we use dx, the infinitesimal delta x, to calculate the area in integration. If dx is in fact infinitesimal, and that's what it means, then it's only as wide as a single line, right? The change in x would collapse down to a point, or the width of a single line. So let's just take a look at this particular, this is a trapezoid here. And let's say that, what would we use as the height of the trapezoid? The short side or the tall side? The y1 or the y2 values? Now the y average is the one right in between. And I guess, we could average out the y values for all those trapezoids, but if we have an infinitesimal number of trapezoids, that'd be a lot of calculating. Couldn't really do that, could you? What we can do, though, is say that if the trapezoids are infinitely thin or infinitesimal in thickness, y1 and y2 become the average y. So we're determining the thickness of a point for our dx. So if you use dx, if it's infinitesimal, the trapezoid is only as wide as a line. So it doesn't matter that there's a curve at the top. y1 and y2 would be meaningless. They would all be as wide as a line. So the fact that the shape is a trapezoid wouldn't matter at all. And then it also wouldn't matter if you have a curve. Now, if you understand integrals already, hopefully that's a nice review. And if you don't understand integrals, again, that's okay. You don't necessarily need to know calculus to be able to do chemical kinetics. But I think it is useful to understand why integrals are important to us. Let's say that we have a graph of velocity versus time. Velocity in meters per second and time in seconds. And as very often happens in nature, things change along a curve. Let's say that you're running a race and you start running very fast, so your velocity is very big, right? We have, high velocity early on, and then as you're running the race, you slow down because, you're getting tired, so your velocity is smaller. And we have this kind of a curved line. We could say that the integral from 0 to any x value of f of x dx would be whatever the equation for the line was in meters per second multiplied by dx, the infinitesimal change on the x-axis in seconds. That would tell us the displacement meters. So if we graph that out, we could determine the area under the curve by doing an integral, and that would allow us to see how far you ran, the meters of displacement that you went through. Or let's say that we're looking at another type of a rate. Again, we like to do integrals when we have some type of a rate versus time. Let's say that you start your career at some lower salary, and then as you move your way through your career, you get more raises, and at some point you kind of max out, and you get to the point in your career where your raises are not happening as much. You're at your maximum salary, and you want to know, can you retire? And let's say you predict, before you even get out here, how much money you might have. It'd be nice to know that, right? Well, what you could do is you could integrate the area under that curve if you knew what that curve was going to look like. And the f of x would be the y value, or the dollars per hour that you're earning. The dx would be in terms of the hours that you've worked. And if you multiply that out, you'd get the dollars. You'd get the overall earnings over your entire career. That'd be something you'd want to know if you want to plan out when you can retire. Let's say that we have a rate of reaction in molarity per second against time. We could do an integration, even if we didn't have a flat line, if we had a line angling down or some type of a curve, which happens in these different rate expressions. We sometimes get lines that angle down, which aren't too bad. You could still use a little algebra for that. But if you have a curve, you have to use calculus for that if you want the area under the curve. That would give us the concentration of that chemical. So instead of graphing and trying to figure out the area under the curve that way, what we do is we use the differential rate law, which tells us how rate relates to concentration, and we integrate that. We do calculus. Integrating the differential rate laws, rate equals k times the concentration of A, rate equals k times concentration of A squared, and we do that to get the integrated rate laws. We're going to take a look at what integrated rate laws look like in the next few videos.